Hello, welcome to a brand new topic called roots of polynomials. But the good news is, despite this being a new topic, it's mostly dealing with ideas that we've already introduced before. For instance, in the case of this video, looking at the roots of a quadratic, for instance. And you might be tasked with doing some mathematics with the roots of that particular quadratic, which might make you think, well, then I'll just find what the roots are, because at this stage I'm expecting you already know how to find the roots of ultimately any quadratic, whether it's one with two real roots, one repeated root, or two complex roots. But just because we can find the roots doesn't mean we should. Because, for instance, for the quadratic we can see on the screen right now, the roots of this particular quadratic are x is equal to 27 plus or minus 3 root 41, all divided by 20, which is a bunch of horrible numbers to have to be doing any calculations with. Okay, in modern times we've got calculators to do it for us, but still, even just typing that out is a bit annoying to do if you have to do it a lot. But if you're trying to do calculations with the roots of a quadratic, sometimes you don't have to find the individual roots themselves to be able to do the calculations you need to be able to do, because some other things related to the quadratic will still be related to the roots while still being nice numbers. For instance, the roots of this quadratic added together would be 27 plus 3 root 41, all divided by 20, plus 27 minus 3 root 41, all divided by 20, which if you add together comes to just 27 over 10, which is a fraction, but it's a relatively nice one because it's only the decimal 2.7, really not that bad to deal with at all. And similarly, it's not just the sum of the roots that ends up being nice for this quadratic. The product of the roots surprisingly also ends up being really nice too, because if you do 27 plus 3 root 41 all divided by 20 times by 27 minus 3 root 41 all divided by 20, then that interestingly just becomes 9/10, which is also really quite a nice number, relatively speaking. So basically the idea of this chapter is that it's not always in your interest to find the individual roots themselves, and instead find what the sum of the roots are going to be and what the product of the roots are going to be, and then try to do whatever maths you need to do with those two results instead, because they'll be much nicer numbers. But how are we going to find what the sum of the roots are and the product of the roots are without finding what the actual roots themselves are individually? Well, let's take a look at a more simple quadratic to illustrate this. We could look at the quadratic x squared minus 5x plus 6 equals 0. And I'm assuming by now you'd be very comfortable in quickly finding the roots are x equals 2, x equals 3. But one such method you might use to find them might be factorizing. Because this quadratic is one with a coefficient of 1 in front of the x squared, the numbers we see inside the brackets for the factorized form are directly linked to what you see as the roots. And interestingly, when you multiply out these brackets to try to get back to the original quadratic, what you'd end up with eventually is x squared minus 2 plus 3 lots of x plus 2 times by 3 on the end equals 0. You can probably straight away start to see how the sum of the roots is related to the coefficients in the actual quadratic, and also what the product of the roots are related to on the end. But what happens if you don't have a quadratic that's got a coefficient 1 in front of x squared? For instance, the general quadratic ax squared plus bx plus c equals 0. Well, because this is a quadratic equation rather than a quadratic expression, we are able to scale it down to being one that's only got a coefficient of 1 in front of the x squared, as long as we do an action to both sides of the equation to keep it balanced. For instance, in this case, we could divide both sides of the equation by a, because then we'd end up with this as our quadratic instead. Therefore, if we knew that the equation had the roots x is equal to alpha and x is equal to beta, those are Greek letters, it's worth pointing out, not to be confused with the letters A and B, so I have drawn my A purposely different because it's not an A, it's the Greek letter alpha. But what that means is if we knew our quadratic had a coefficient of 1 in front of x squared, then we know the roots alpha and beta would relate to what it was factorizing to, x minus alpha, x minus beta. And if you were to then multiply out the brackets in that case, then the quadratic would be rewritten as x squared minus alpha lots of x minus beta lots of x plus alpha times by beta equals 0. And what that would mean is that we'd end up with x squared minus alpha plus beta lots of x plus alpha beta. The reason this is interesting is because it now means we can compare what we got for our quadratic in terms of alpha beta in comparison to what was the original coefficients of the quadratic, which is, in this case, b over a as the coefficient of x. Similarly, we can compare the constant term of our original quadratic, or at least the scaled down version, to what we got in terms of alpha beta on the end of our quadratic as well. By comparing the coefficients of the two quadratics in this way, that leads us to be able to say that the general quadratic with the formula ax squared plus bx plus c equals 0, having roots alpha and beta, must therefore tell us that alpha plus beta, the sum of the roots, must equal minus b over a. And the product of the roots, in other words alpha times by beta, must be equal to c over a. And therefore, just by looking at the coefficients of the original quadratic, we can very easily work out the sum of the roots of that quadratic, in this case alpha plus beta, and also the product of the roots, in this case alpha times by beta, without ever individually calculating what the values of alpha and beta are, therefore avoiding ever having to deal with really nasty numbers in your calculations. So let's put this knowledge into practice by taking a look at an example. So we've been given the quadratic 5x squared plus 3x plus 8 equals 0 has the roots alpha and beta. And we've been specifically told that without calculating the values of alpha and beta, we need to then find the values of all these other expressions that are in terms of alpha and beta. So it's worth noting this question has almost tried to hint to us in several ways that this is a roots of polynomials question. First by mentioning these Greek letters alpha and beta, which is often associated with this topic, but also because they are saying without calculating what those roots are individually. And therefore to use as building blocks, we can start by just working out what the value of alpha plus beta would be by realizing it's going to be minus 1 lots of the value of b, 3 divided by the value of a, 5, and also work out the value of alpha times by beta, which is just going to be the value of c, which in this case is 8, divided by the value of a, which is 5. Nice, so we can now use these things to work out the values of the things we're trying to calculate in part A, part B, and part C. So in part A, for instance, 4 alpha plus 4 beta plus 11 is going to equal, more simply, factorising that 4 out of the first two terms, gives us 4 lots of alpha plus beta plus 11. Which is great because we know what the value of alpha plus beta is. So it's just going to be 4 lots of minus 3/5 plus 11, which is going to be minus 12/5 plus 11, which is just going to quite simply be 43 over 5. Part A done. On to part B, where we now need to calculate alpha cubed beta cubed, which might look scary until you realise there's a really handy index law that makes it easy, which is just to realise that if you have two things multiplied together then taken to a power, you can take those things to that power individually and then multiply them. So therefore meaning we just need to do alpha beta all cubed to work out what we wanted, which is just going to be 8/5 all cubed. That comes to 512 divided by 125. On to part C, and all we're going to do is basically the same thing we've been doing before. Rewrite this expression in terms of the sum of the roots and the product of the roots. So we can just start by creating a common denominator to re-add these fractions together, which will get us this and this. And then when we combine the fractions, we realize we just need to do 7 lots of alpha plus beta, all divided by alpha times by beta. Cool. So therefore that's just going to be 7 lots of minus 3/5, all divided by 8/5. And if you were to work out what that's going to be, it's just going to be minus 21 over 8. Nice. Example 1 done. However, I've got another example for you as well, and this one is going to deal with the fact that a lot of students often come up to me and ask why do the questions that they have to try always be so much more difficult than the examples they're shown. So, tell you what, here's a tricky example. We've been given a quadratic which has got roots alpha plus 1 and 3 alpha. Although we don't have an alpha and a beta written there, just because we've got the words roots and anything to do with the letters alpha or beta is kind of enough to give us already a clue the fact that this is a roots of polynomials question. Interestingly though, this time the question doesn't specify that we must not calculate the roots individually, but that's partly just because there is no way to instantly calculate the roots just from the beginning of the question because of the presence of the k in the quadratic itself. But it is worth noting that if you did want to work out the roots as part of doing other algebra to solve this question, then you could, and you wouldn't be punished for it in this particular case because of the wording. But actually you wouldn't have to, as you'll see right now. So, we might not know how to start off this question, but therefore a good thing to start with is just anything we know how to do with quadratics and roots, which is, as we've just been discovering in this video, how to work out the sum of the roots for a particular situation. So in this case, the sum of our roots would be alpha plus 1 plus 3 alpha, and therefore that's going to be equal to minus b, so that would be minus 19 over our a, which in this case is k, which of course comes to 19 over k, meaning we have that 4 alpha plus 1 is equal to 19 over k. We then also have the fact that we can work out the product of the roots, which is just going to be 3 alpha times by alpha plus 1, and that's meant to come to our c over a, which is 28 over k, meaning we get that 3 alpha squared plus 3 alpha is equal to 28 over k. And therefore we've now got a situation that's effectively boiling down to simultaneous equations between this and this, where we need to find the values of k. So let's go ahead and do that. So starting off by taking away 1 from that equation that's got 4 alpha involved to get 19 over k minus 1, and then dividing by 4 to get alpha is equal to 19 over 4k minus 1 over 4. So substituting that into the other equation, we'll get 3 lots of 19 over 4k minus 1/4 all squared. We'll end up with plus 3 lots of 19 over 4k minus 1/4, and that's got to equal our 28 over k. Nice. So, although this looks really horrible, and I won't lie to you, it's not going to be particularly nice to do, it's just a bunch of algebra. So let's start by multiplying out those brackets with the power of 2 there. So therefore that will be 361 over 16k squared on the denominator. We're going to end up with minus 19 over, it would be 16k, but times it by 2, so it's just going to be an 8k. And then we've got a plus 1/16. Then we've got a 3 times by 19 over 4k, which is just going to be 57 over 4k. We're going to end up with minus 3/4, and then that's still equal to 28 over k. Multiplying out more of the brackets will get us 1083 over 16k squared minus 57 over 8k plus 3/16 plus 57 over 4k minus 3/4, and let's move that 28 over k onto the other side. So it's now equal to 0. This looks really horrible, and you could choose to just gather this stuff together at this stage, whatever suits you, but I am going to multiply both sides by 16k squared, partly because I'm going to want to multiply both sides by k squared to turn it into an ordinary quadratic anyway, but also if I times everything by 16, I don't have to deal with horrible fractions anymore. So therefore that will give me 1083 minus 114k plus 3k squared plus 57 over 4k times by 16k squared, which would be 228k minus 12k squared, and then lastly 448k. So that's everything multiplied through by 16k squared. Be really careful when doing that sort of algebra stuff. Take your time if necessary. Right, we can now gather like terms together, so therefore we're going to end up with minus 9k squared. We're going to end up with 114k, take away 448, which comes to minus 334k. And then lastly, we've just got that 1083. So we've just got to solve that quadratic to find what k is. So I'm going to use the quadratic formula, of course, just because in reality I'm using the calculator to do it for me. But as this is what the calculator is secretly doing when I do it, this is why I write the quadratic formula out. Just to make sure we get the method marks. Cool, so therefore that will lead to the answers. K is equal to minus 361 over 9, or k is equal to 3. And there you go, we solved it. Blimey, that was a lot of work, but it goes to show you how you can use roots of polynomials to solve even some more slightly tricky problems. Okay, that will do us for today's video. We've got a lot more to explore though in this chapter, so stay tuned for the future videos on this topic. See you in the next one. Goodbye.